Good morning, class. Today I'm going to cover the last two examples that I'm going to cover for the project. Here we are. We're going to talk about elastic and connected masses today, and I'm going to show a way to make an example for each one of these. So for our elastic situation, one thing we know is that all elastic forces are going to be following Hooke's law. So Hooke's law, if you hopefully remember, is that an elastic force will be equal to a value k called the spring constant multiplied delta x, which is the distance that it's stretched, or the distance change from equilibrium. So one of our problems, we have to find either the spring constant or the distance change from equilibrium. One thing for us to consider is that all elastic forces are done considering the situation has balanced forces, or are done in a singular instant of time. That's because if the forces are not balanced, or we're looking for a long range of times, is that elastic, that spring, might be changing in how far it's stretched or how far it's squished. If that's the case, then that means the elastic force is constantly changing. And we haven't dealt with changing values yet, and we don't have the mathematical tools to deal with that at this moment. So all of the situations that you're going to think of using elastic forces are going to be where the objects are at rest. So hopefully that will help you when making up a situation. Let's imagine that there's a situation. There is a box, and if I want it attached to an elastic source, then I'll attach it to a spring. And that spring, it could be attached to a wall, for example. Uh, Now, what am I going to imagine here? How can I make up a situation where it's solved, where I have to solve for the spring constant? Well, there are a couple things I could do. I want to consider this problem when the forces are balanced, and I want the elastic force to be part of that, because if I don't have the elastic force to be part of that, I can't solve for the spring constant or the distance change from equilibrium. So I'm going to immediately assume that I've already stretched or compressed my spring. Let's say I've stretched my spring, just because. Now, if this is set on the ground, I also know that the ground usually provides friction. So maybe I might know exactly how much friction this block is under, and I want to know how far I can stretch my spring from equilibrium. That would solve for my second part, right? I want to know, hey, how far can I stretch my spring without it getting bigger than friction? That's something that we could just kind of make up. So let's make this our question. Now that might be like a good question, but the problem is we don't have any information. So this problem isn't close to solvable yet. Let's go ahead and give ourselves a free body diagram so we can actually figure out what's going on. If we stretch the spring wants to pull back inward, so I'll go Fe for F elastic. Now looking at this, we're like, all right, this is a decent free body diagram, and if I considered the direction of motion, it'd be left and right. So the net force is going to be my left and right forces. That'll be my elastic force and my friction force. Now, if I think of this question, how far I can stretch a spring, this actually considers a balance force situation, because the last moment that the forces end up being balanced is that tipping point, right? That tipping point of how far. So balance forces tells me that my acceleration is 0. So I'll have the mass of this object times an acceleration of 0. Now, what things do I need to know to help me? Well, let's break down each of these formulas to help us figure out. The elastic force is solved with K times delta X. And the friction force has a formula of mu, the coefficient of friction, times the normal force. Okay, I'm going to grab my red marker here. Let's see what we have. Uh, delta X is the thing that we're going to need to know, right? That's what we're trying to find out. That's the how far. So that's fine. We can leave that as an unknown value. What do we need to figure out? It looks like I'm going to have to need to be told my K. So in the problem, I'm going to have to give my K value. I'm also, and that will tell me that, I also am going to have to tell the coefficient of friction. That's another thing that I'm going to have to include in my problem. The normal force is also the unknown. Now, usually people don't just say, oh, here's the normal force, right? Usually you'll have to determine what the normal force is from the situation. So let's look at the normal force. The normal force is currently balancing the force of gravity in this particular situation. That means if we have a way of finding the force of gravity, m times g, we have a way of finding the normal force, and by finding the normal force, that'll give us the last thing. So what do we need to find that? Oh, we need to know the mass. Knowing the mass will give us our gravity, and that'll give us a normal force. And that'll get us this mass, though that doesn't matter as much because anything times 0 is 0. Anything times 0 is 0. There we go. So if I make my word problem to include the spring constant, the coefficient of friction, and the mass, that will be all I need to solve for this elastic force problem. I've had some people asking me to remind them, what is the elastic force about? The elastic force is a force provided by a spring or a stretchy rope. And all that spring is trying to do is just return back to its equilibrium position. In other words, if you stretch a spring, it wants to pull back to being short. If you squeeze a spring, it wants to push back to being its original size. It is a force. That's all it is, and it acts just like any other force. So don't think it follows any special force rules. It only has a formula, right? It only has a formula, Hooke's law. So if you see an elastic force, you know the elastic force can get this formula. Let's look at connected masses. So connected masses has been this new topic that we've covered during our distance learning. Thing is that it doesn't apply anything super brand new. All it's doing is it's making us expand our view of more than one object. So let's try to make a connected masses problem. One problem must involve a situation where one of the masses is unknown and must be found. How would I make up a situation like this? Well, first let's imagine a situation that may have two masses that are connected by ropes. And I'm going to go out of my way to change the direction using a pulley because I find that is going to be one of the most helpful ways for us to really learn is by challenging ourselves a little bit by changing directions of forces using a pulley. So we have two masses. Now one of the masses is unknown. So I'm going to call this one 5 kilograms and I'm going to call this one M because I don't know what that mass is. And if I call this mass A, the 5 kilogram mass is mass A, and the M mass is mass B, there we go. This gives me my situation. You could say two masses are attached to an Atwood machine, or you can see that these would act kind of like an elevator and counterweight, or you could just describe two blocks are attached by string and hung over a pulley. And you can provide a little diagram to help your situation. It's fine to help your description. So now that we've imagined a situation, let's just include what are the outside forces on this system, on all of the pieces. Well, it looks like there's gravity on this, and there's gravity on B as well. There's gravity on A, and there's gravity on B. I think those are the only forces that are considered outside forces. So if that's the case, then we can make a net force equation to look at the entire system. F net equals. Now here's the thing. How do these forces interact? Are they working together because they're both down? Hopefully, you're saying to the screen, no, Mr. Westergaard, if you pulled mass M down, that has to lift the 5 kilogram mass. And the opposite is also true. Oh, so that means my forces go up and down like this. And the direction down on opposite sides of the pulley is working against each other. So we need to choose one to be winning, just arbitrarily. For the sake of argument, I'm going to say that 5 kilogram mass is winning and the M is not. So looking at my net force equation, that means FGA minus FGB. Now this is all well and good, but normally, like usual, is I don't give you gravity forces in a word problem just as the gravity force. You're going to have to give me a way to solve for it. So that means we need to break down these pieces into what we've got. So we know the net force is the mass times acceleration, but remember, when you have connected masses, both masses, the 5 times the m, are going to be moving. So if both masses are going to be accelerated, we have to include both of them added together for our net force mass. So that's our mass times our acceleration, right? This is m times a. It's just the total mass times a. FGA, FGA is going to be our mass A times 9.8, or 5 times 9.8. And FGB is going to be mass B times 9.8, or M times 9.8. So when we look at this problem, we want only one unknown. 5, check mark. M is our unknown. That's what we're looking for. A, we're going to need to provide the acceleration in the problem. Maybe we're going to say that the 5 kilogram mass is accelerating downward at 1 meter per second squared. Okay, that would give me my A now. So we know we're going to need to include A. Now let's look at the rest. 5, yep, we got it. 9.8, we got it. M, note this M is the same mass that we're looking for. It might be in two places, but that's just the challenge of this problem. So that's fine. And 9.8. There we go. All I need to do now is use my imagination and use a little bit of words to make this into a word problem. But now that I know that I need to include my acceleration for me to find my unknown mass, I have everything I need to help me make a problem about connected masses. I hope these little example videos have been helpful. Please work hard on this review package. That is one of the key things that's going to be helping you, as well as helping me understand, what you know. Have yourself a good day, everyone.